So today I'm gonna do the computer vision course. I'm gonna do 2 hours now, maybe 2 hours tomorrow. I don't think I'm gonna, yeah. And then later on I might come back and watch some videos and continue on the other stuff I'm doing. So let's start the timer. Welcome to Computer Vision. Have you ever wanted to teach a computer to see? This course is exactly what you will do. In this course, you will use modern deep learning networks to build an image classifier with Kernels, design your own custom convert with reusable blocks, learn the fundamental ideas behind visual feature extraction, master the art of transfer learning to boost your models, utilize data augmentation to extend your dataset. If you've taken the introduction to deep learning course, you'll know everything you need to be successful. This course will introduce you to the fundamental ideas of computer vision. Our goal is to learn how a neural network can understand natural image well enough to solve the same kinds of problems the human visual system can solve. Neural networks that are best at this task are called convolutional neural networks. Sometimes we say convnet or CNN instead. Convolution is the mathematical operation that gives the layers of a convert. The mathematical operation that gives the layers of a convnet their unique structure. In future lessons, you'll learn why this structure is so effective at solving computer vision problems. We apply these ideas to problems of image classification. Given a picture, can we train a computer to tell us what it is? We may even set apps that do that. Okay, convolutional classifier. Not used for image classification consists of two parts: convolutional base and a dense head. So image, base, extract, head, classify, class output. The base is used to extract features from an image. It is formed primarily it is formed primarily of layers performing the convolutional operation, but often includes other kinds of layers as well. The head is used to determine the class of the image. It is formed primarily of dense layers, but might include other layers like dropouts. What we mean by visual feature: a feature could be a line, a color, a texture, a shape, a pattern, some complicated combination. The whole process goes something like this. I wonder if it's possible to build something that gives another sense. It would be interesting to think about that. If AIs can model visual, then probably can model touch as well. Touch, hear, the five senses, and maybe they can create new ones, which is an interesting concept. Features actually extracted look a bit different, but it gives the idea. Training the classifier. The goal of the network during training is to learn two things: which features to extract from an image base, which class goes with what features had. These days, convnets are rarely trained from scratch. More often, we reuse the base of a pre-trained model. To the pre-trained base, we then attach an untrained head. In other words, we reuse the part of a network that has already learned to do one. Extract features and attach to it some fresh layers to learn to classify. So I have the features, you have classes, we'll have all classes. Because the head usually consists of only a few dense layers, very accurate classifiers can be created from relatively little data. Using a pre-trained model is a technique known as transfer learning. It is so effective that almost every image classifier these days will make use of it. Throughout this course, we're going to, let me load the training part before I continue, so it's faster. Throughout this course, we're going to be creating classifiers that attempt to solve the following problem. Is this a picture of a car or of a truck? Our dataset is about 10,000 pictures of various automobiles, around half cars and half trucks. So step one, load the data. Is next cell, we import the things, and then split the training. So splitting the data first. Which is different than other problems because it's not a pandas data frame, apparently. Oh, it looks like it might be sort of like a pandas data frame, but made out of images instead. Data pipeline converts float image label. So this converts the image to numbers, which is probably gonna be a matrix of matrix of pixel values that are three-dimensional because they have color to them and XY position. If I remember correctly, there are layers that determine the colors, but I'm not really sure about that. Let's take a look at a few examples from the training set. Define pre-training base. The most commonly used data set for pre-training is ImageNet, a large data set of many kinds of natural images. Keras includes a variety of models pre-trained on ImageNet and its application module. The pre-trained model we'll use is called VGG16. So TF Keras models load model. Pre-trained base trainable false. That's Chad. Next, we attach the classifier head. For this example, we use a layer of hidden units. The first dense layer, followed by a layer to transform the outputs to a probability score for class 1 truck. The flattened layer transforms the two-dimensional outputs of the base into the one-dimensional inputs needed by the head. So let me read this again. Hidden unit, a layer of hidden units, first dense layer, followed by a layer to transform the outputs to a probability score. So it's the same as before. It's gonna use a sigmoid for the output and ReLU for the hidden layers. Latent layers transform the two-dimensional outputs of the base into the one-dimensional inputs needed by the hand. The flattened layer transforms the two-dimensional outputs of the base to the one-dimensional inputs needed by the hand. Not exactly sure how this works. Apparently it's not loading. Let me just load this train. So it's pretty much like the other cars, just with it. The only difference is pre-trained based here, which is this model that is attaching to this one. Oh, so now I get it. The the output of the pre-trained model is gonna be two-dimensional, and the point of the first layer should translate that two-dimensional output into one. I guess that's what's happening. Finally, let's train the model. Since this is a two-class problem, we'll use the binary versions of cross-entropy and accuracy. The Adam optimizer generally performs well, so we'll choose it as well. So Adam optimizer, I've looked at it into it after I streamed, and is just a variation of stochastic gradient descent. And there's a bunch of variations but they change is pretty much how fast and slow you approach the gradient. how big the steps are, and the momentum changes, stuff like that. So yeah, some have randomness, some are more deterministic, and some change the momentum at different parts of the algorithm. That's pretty much the differences between them. So you're just gonna use Adam, binary cross entropy, matrix binary accuracy. History equals model fit. Yes string. Relation data equals yes valid. Epochs 30. So it doesn't need to specify batches in this case because it's an image. When training a neural network, it's always a good idea to examine the loss and metric plots. History object contains information in a dictionary. You can use pandas to convert. So here's analyzing. So here it seems like it's overtraining. Maybe. Conclusion. In this lesson, we learned about the structure of a Convolutional classifier. A head checked as a classifier atop of a base which performs a future extraction. So the head classifies and the base uh, learns the futures of different small patterns that make up most images. Damn, this first part is massive. The head essentially is an ordinary classifier like you learned about in the introductory course. For futures, it uses those futures extracted by the base. It's the basic idea behind convolutional classifiers. That we can attach a unit that performs future engineering to the classifier itself. This is one of the big advantages deep neural networks have over traditional machine learning models. Given the right network structure, the deep neural net can learn how to engineer the features it needs to solve this problem. In the next few lessons, we'll take a look at how the convolutional base accomplishes the feature extraction. Then you'll learn how to apply these ideas and design some classifiers of your own. So here you have random seeds to create the data, to separate the data, maybe. Then the matplotlib stuff to determine the style of the graph. The train is the image, the training part, the S train. Validation is the validation. So it's loading from this directory, applying labels, batch size 64. Well, it's interesting that here there's a batch size, but in the model it's not necessary. Data pipeline converts to float. I'm not sure if I don't remember really well if mini batch I forgot the name of the thing. I forgot the name. I think mini batch. It's mini batch something to normalize the data, and is if I forgot if that's just for regression problems and not for classifier. Don't remember really well. It was mini batch something. I forgot. Not I remember now. Then converts the image to a float. Yeah. I think it was mini batch randomization, something like that. Forgot. But It's basically a method for the model to rescale the data, normalize the values in batches instead of doing the whole thing before. I'm not sure if this works only for regression or classifier problems. Define pre-trained base. Now that you have a pre-trained base to do a feature extraction, decide whether this base should be trainable or not. Yeah, I'll have to look at the tutorial again. Should be trained. I don't remember this stuff. So it's either false or true. So they make it false here, but it doesn't explain why it's false. Oh, I think it's false because you don't want the model to modify the training base. That's the reason. So you have to put it true when you want the model to modify. Because as it trains, you can't change the weights of the training base. Otherwise, it would fit the point of having the training base. Doing trust learning is generally not a good idea to retrain the entire base, at least not without some care. The reason is that the random weights in the head will initially create large gradient updates, which propagate back into the base layers and destroy much of the pre-training. Using techniques known as fine-tuning, it's possible to further train the base on new data, but this requires some care to do well. Dataset. Now that the base is defined to do the future extraction, create a whole head of dense layers to perform the classification, following this diagram. So it's pretty much like the other models from the introductory course. I can just it's activation. Oh. I'm not sure if I have to put an input here, but I don't think so. Sigmoid. Let me remember here. Layers flattened. It's already here. So this is the first layer that translates the two outputs into one binary input. Into one input. Train. Before training a model in Keras, you need to specify an optimizer. Loss is gonna be binary cross entropy. Binary classification. And I forgot the metrics. I think it's binary cross entropy as well. Binary accuracy. It's underlined. Not. On the side below, to plot the loss metric per course. So I forgot to run this. So it's fitting the model to the training in the validation set on 30 epochs. And mini batch. Keras. I think I'm gonna look for this because I forgot. Batch size. No, wasn't batch size. Batch normalization, mini batch normalization. It's probably. I'm gonna be right back. This is probably gonna take some time. So, right back. This might take a long time, actually. It's only at 3 of 30. I wonder if I can keep going about this training. Maybe I can watch the videos on Random Forest while I wait for the thing to finish. So it's not showing here. Maybe train on batch method is gonna have. Yeah, batch size, I think. It was the thing. But I remember I have seen mini batch something. Maybe I could just go to the course and see again. I think it's easier to see. This isn't far forward. Still. And I can't run the other one. Completed. Batch normalization. Yeah, batch was batch normalization. And batch size. So do I need to run this all? I think I'm gonna stop and see if I can continue. Yeah. The only way to go about it is by training. And then still on the first part. If I knew this, I should have started before reading the tutorial. I think what I'm gonna do is watch some videos while I wait for that to finish.
StatQuest is growing up. StatQuest is growing down. StatQuest is growing. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to be talking about decision trees. Here's a simple decision tree. If a person loves StatQuest theme songs, then that person is awesome. And if a person does not love StatQuest theme songs, then that person is slightly less than awesome. In general, a decision tree asks a question and then classifies the person based on the answer. It's no big deal. This decision tree is based on a yes-no question. But it is just as easy to build a tree from numeric data. If a person has a really high resting heart rate, then that person had better see a doctor. And if a person does not have a super high resting heart rate, then that person is doing okay. Here's one more simple decision tree. This decision tree is based on ranked data, where 1 is super hungry and 2 is moderately hungry. If a person is super hungry, they need to eat. And if a person is moderately hungry, they just need a snack. And if they are not hungry at all, then there's no need to eat. Note, the classification can be categories or numeric. In this case, we're using mouse weight to predict mouse size. Here's a more complicated decision tree. It combines numeric data with yes. You start at the top and work your way down. But there are no arrows pointing away from them. Now we are ready to talk about how to go from a raw table of data to a decision tree. In this example, we want to create a tree that uses chest pain, good blood circulation, and blocked artery status to predict whether or not a patient has heart disease. The first thing we want to know is whether chest pain, good blood circulation, or blocked arteries should be at the very top of our tree. We start by looking at how well chest pain alone predicts heart disease. Here's a little tree that only takes chest pain into account. The first patient does not have chest pain and does not have heart disease, and we keep track of that here. The second patient has chest pain and heart disease, and we keep track of that here. The third patient has chest pain but does not have heart disease. The fourth patient has chest pain and heart disease. Ultimately, we look at chest pain and heart disease for all 303 patients in this study. Now we do the exact same thing for good blood circulation. Lastly, we look at how blocked arteries separates the patients with and without heart disease. Since we don't know if this patient had blocked arteries or not, we'll skip it. However, there are alternatives that I'll discuss in a follow-up video. Remember, the goal is to decide whether chest pain, good blood circulation, or blocked arteries should be the first thing in our decision tree, aka the root node. So we looked at how well chest pain separated patients with and without heart disease. It did okay, but wasn't perfect. Most of the patients with heart disease ended up in this leaf node, and most of the patients without heart disease ended up in this leaf node. Then we looked at how well good blood circulation separated patients with and without heart disease. It wasn't perfect either. Lastly, we looked at how well blocked arteries separated patients with and without heart disease. Note, the total number of patients with heart disease is different for chest pain, good blood circulation, and blocked arteries because some patients had measurements for chest pain, but not for blocked arteries, etc. Oh no, it's another one of those ghastly jargon alerts. Because none of the leaf nodes are 100% yes heart disease or 100% no heart disease, they are all considered impure. To determine which separation is best, we need a way to measure and compare impurity. There are a bunch of ways to measure impurity, but I'm just going to focus on a very popular one called Gini. To be honest, I don't know why it's called Gini. I looked around on the internet and couldn't find anything. However, if you know, please put it in the comments below. I would love to know. Regardless, the good news is calculating Gini impurity is easy. Let's start by calculating Gini impurity for chest pain. For this leaf, the Gini impurity equals 1 minus the probability of yes squared minus the probability of no squared. Now let's plug in some numbers. The probability of yes equals 105 divided by the total number of people in this leaf node. And the probability of no equals 39 divided by the total number of people in this leaf node. After we've done the math, we get 0.395. That is to say, the Gini impurity for the leaf node on the left equals 0.395. Now let's calculate the Gini impurity for this leaf node, the one on the right. Just like before, it equals 1 minus the probability of yes squared minus the probability of no squared. And the probability of yes is 34 divided by the total number of people in this leaf node. And the probability of no equals 125 divided by the total number of people in this node. And if we do the math, we get 0.336. Now that we have measured the Gini impurity for both leaf nodes, we can calculate the total Gini impurity for using chest pain to separate patients with and without heart disease. Because this leaf node represents 144 patients, and this leaf node represents 159 patients, the leaf nodes do not represent the same number of patients. Thus, the total Gini impurity for using chest pain to separate patients with and without heart disease is the weighted average of the leaf node impurities. So to calculate the weighted average, we take the total number of people in the left leaf node and divide it by the total number of people in both leaf nodes. We then multiply that fraction by the Gini impurity for the left leaf node. Then we take the total number of people in the right leaf node.
So it's very similar to deep learning neural networks. It's basically a weighted distribution, weighted sum.
Divided by the total number of people in both leaf nodes.
But yeah, it's slightly different.
And then multiply that fraction by the Gini impurity for the right leaf node. After we do the math, we get 0.364. Thus, the total Gini impurity for chest pain equals 0.364. And since I'm such a nice guy, I'm going to cut to the chase and tell you that the Gini impurity for good blood circulation equals 0.360. And the Gini impurity for blocked arteries equals 0.381. Good blood circulation has the lowest impurity. It separates patients with and without heart disease the best. So we will use it at the root of the tree. Patients with good circulation. Do these new leaves separate patients better than what we had before? So far, we've seen how to build a tree, and then we calculate the impurity values for the ranked data as well as each possible color choice is blue or red.
I think what I'm gonna do is continue with the tutorials, and I'll finish this later. It's better. Because here's just the checking part. I'm afraid that if I click this, it's gonna start from the beginning again. Thank God it didn't. Convolutional ReLU. In the last lesson, we saw that a convolutional classifier has two parts, a convolutional base and a head of dense layers. We learned that the job of the base is to extract visual features from an image, which the head would then use to classify the image. Over the next few lessons, we're going to learn about the two most important types of layers that you usually find in the base of convolutional image classifier. These are the convolutional layer with ReLU activation and the maximum pooling layer. Lesson 5, you'll learn how to design your own convnet by composing these layers into blocks that perform the feature extraction. This lesson is about the convolutional layer with its ReLU activation function. Feature extraction. Before I get into the details of convolution, let's discuss the purpose of these layers in the network. We're going to see how these three operations, convolution, ReLU, and maximum pooling, are used to implement the feature extraction process. The feature extraction performed by the base consists of three basic operations. Filter an image for a particular feature, convolution. Detect that feature within the filtered image, ReLU. Condense the image to enhance the features, maximum pooling. The next figure illustrates this process. You can see how these three operations are able to isolate some particular characteristic of the original image, in this case horizontal lines. So I have the image, the input, filter, detect, condense. The tree is, typically the network will perform several extractions in parallel on a single image. In modern convnets, it's not uncommon for the final layer, the base, to be producing over 1,000 unique visual features. Filter with convolution. A convolutional layer carries out the filtering step. You might define a convolutional layer in a Keras model, something like this. Layers conv2, filter 64, kernel 3. The brilliant course, they talk about this a little bit, and how it actually works, the steps, and the mathematics. We can understand these parameters by looking at their relationship to the weights and activations of the layers. The layer. Let's do that now. The weights a convnet learns during training are primarily contained in its convolutional layers. These weights we call kernels. We can represent them as small arrays. A kernel operates by scanning over an image and producing a weighted sum of pixel values. In this way, a kernel will act sort of like a polarized lens, emphasizing or de-emphasizing certain patterns of information. Kernels define how a convolutional layer is connected to the layer that follows. The kernel above will connect each neuron in the output to 9 neurons in the input. By setting the dimensions of the kernels with kernel size, you are telling the convnet how to form these connections. Most often, a kernel will have odd numbered dimensions, like kernel size equals 33 or 55, so that a single pixel sits at the center, but this is not a requirement. The kernels in a convolutional layer determine what kinds of features it creates. During training, a convnet tries to learn what features it needs to solve the classification problem. This means finding the best values of its kernels. Activations. The activations in the network we call feature maps. The activations in the network we call feature maps. They are what result when we apply a filter to an image with the individual features the kernel extracts. Here are a few kernels pictured with feature maps they produce. From the pattern of numbers in the kernel, you can tell the kinds of feature maps it creates. Generally, with a convolutional what a convolution accentuates its inputs will match the shape of the positive numbers in the kernel. The left and middle kernels above will both filter for horizontal shapes. So yes, pretty much evaluating the pixels. Where was I? With the filter parameter, you tell the convolutional layer how many feature maps you want it to create as outputs. Oops. Detect with value. After filtering, the feature maps pass through the activation function. Rectifier function has a graph like this. Neuron with a rectifier attached is called a rectified linear unit. For that reason, we might also call the rectifier function the ReLU activation and the ReLU function. The ReLU function can be defined in its own activation layer. Most often, you would just include it as the activation function of conv today. So define the same line. You could think about the activation function as scoring pixel values according to some measure of importance. ReLU activation says that negative values are not important. And so sets them to 0. Everything unimported is equally unimported. Here's ReLU applied the feature maps above. Notice how it succeeds at isolating the features. I'm gonna load this stuff. Like other activation functions, the ReLU function is nonlinear. Essentially, this means that the total effect of all the layers network becomes different than what you would get by just adding the effects together. It should be the same as what you could achieve with only a single layer. The nonlinearity ensures features will combine in interesting ways as they move deeper into the network. Apply convolution around. We'll do the extraction ourselves in this example to understand better what convolutional networks are doing behind the scenes. Here's the image we'll use for this example. So image path reads the image, decodes the image into JPEG. And here's plotting. This is the plotting design. And this is the plot. For the filtering step, we will define the kernel and then apply it with the convolution. The kernel in this case is an edge detection kernel. You can define it with the f constant, just like you define an array numpy with np array. This creates a tensor of the sort Tensorflow uses. So it's -1 on the surroundings and 8 at the center. Tensorflow includes many common operations performed by neural networks in its tf.nn module. The two that we will use are conv2d and ReLU. These are simply function versions of Keras layers. This next hidden cell does some reformatting to make things compatible with TensorFlow. The details aren't important for this example. I don't think I'm gonna read this. Maybe some other time. I wonder how do they make money off this? Because it's definitely not for free. You can use it for free, but they're somehow making money probably. Let's apply our kernel and see what happens. Oh, that's pretty good. Input image filter scanner. Next is the detection step with the ReLU function. This function is much simpler than the convolution, as it doesn't have any parameters to set. And now we've created a feature map. Images like this are what they had used to solve its classification problem. You can imagine that certain features might be more characteristic of cars and others more characteristic of trucks. The task of a ConvNet during training is to create kernels that can find those features. conclusion, we saw in this lesson the first two steps that Convnats uses to perform feature extraction, filter with conv2d layers, and detect with rel activation. So here's loading the image, I guess, importing the stuff. You can run this out to see some standard kernels used in image processing. So edge detect, bottom sobal, emboss, sharpen. Define kernel. Use the next code cell to define a kernel. You have your choice of what kind of kernel to apply. One thing to keep in mind is that the sum of the numbers in the kernel determines how bright the final image is. Generally, you should try to keep the sum of the numbers between 0 and 1, though that's not required for a correct answer. In general, a kernel can have any number of rows and columns. For this exercise, let's use a 3 by 3 kernel. So it's pretty much a matrix. I don't think it's two-dimensional. I think it's one-dimensional. And the kernel is pretty much a matrix of pixels that determines a pattern. In general, a kernel can have any number of rows and columns. For this exercise, let's use 3 by 3 kernel, which often gives the best results. Define a kernel with TF constant. With only 2 dimensions, but should define a kernel shape 9. So only 2. So maybe it's this. Be sure to have only one level nesting in your brackets. I think it's 1 for each line, I think. So it is 2-dimensional. Correct. Okay. Now we'll do the first step of feature extraction, the filtering step. First, run this out to do some reformatting for Tensorflow. So it's converting the image to float. I think that's all this cell does. Apply convolution. Now we will apply the kernel to the image by convolution. So we just use this convnat. I don't think it is a list. It's just parentheses. What is the backend function Tensorflow that performs the same operation? So it's df something. Maybe df.conv2. Now apply the kernel to the layer in Keras that does this layers.conv. As the backend function Tensorflow that performs the same operation. I'm not sure if this. So I have to look because I don't remember. And then conv2. Yeah, I think it's Zenon.conf. But it has to be parameters. Did these small steps? The Tensorflow convolutional function without arguments. It's saying it requires arguments. Oh, maybe it's TF and then maybe it's, I don't think it's sigmoid, but TF and then sigmoid. Let me put these arguments and see if it works. I don't think I'm supposed to put this. Filter must be 4-dimensional. They say they will talk about on lesson 4, so. Oh, so it's just this without parentheses. Once you've got the correct answer, run the cell, to execute the convolution, see the results. Filter must be 4-dimensional. Let me see if I did the kernel the right way. It seems to be correct. Why is giving me this mistake? Let me see the solution here. Yeah, that's weird. I think I'm gonna see the solution to this one. So maybe the values that I put are wrong. But it doesn't specify anything about the values. That's what's weird. Now it's saying that it's supposed to be a float. Maybe I didn't run this, so this cell I think is supposed to convert the image to a float. Try to run all the cells. Oh, now it works. Now detect the feature with relu function. In Kernels, you usually use this as activation function in a conv layer. What is the backend function in TensorFlow that does the same thing? tf.nn.relu. Correct? Once you've got the solution, run the cell to detect the features which will answer the results. The image you see below is the feature map produced by the kernel you chose. If you like, experiment with some of the other suggested kernels above, or try to invent one that will extract a certain kind of feature. Throughout our discussion of kernels and feature maps was mainly visual. We saw the effects of Conv2D and ReLU, as over how they transformed some example images. But the operations in a convolutional network, like in all neural networks, are usually defined through mathematical functions for computation on numbers. The next exercise will take a moment to explore this point of view. Let's start by defining a simple array to act as an image, another array to act as a kernel. The following cells. So this is image and then the kernel. Observe a convolutional numerical matrix. What do you see? The image is simply a long vertical line on the left and a short horizontal line on the lower right. What about the kernel? What effect do you think it will have on this image? After you've thought about it, run the software and answer. So it will detect this pattern here, the horizontal line, not the vertical one. The tutorial we talked about how the pattern of positive numbers will tell you the kind of features the kernel will extract. This kernel has a vertical column of ones, and so we would expect it to return features of vertical lines. Now let's try it out, run the cell. Yes, I confused vertical with horizontal, but that's what I meant. So this is gonna take ages probably. Still halfway through. I'll be right back. Well, I'll wait for this. Okay, I'm back. Lesson 2 began our discussion of how the basis in the convnet performs feature extraction. We learned about how the first two operations in this process occur in a conv2d layer with rel activation. In this lesson, we'll look at the third and final operation in this sequence, condense with maximum pooling, which in Keras is done by a maxpool2d layer. Condense with maximum pooling. Adding condensing step to the model we had before will give us this. So it's pretty simple, just put a method there. Maxpool2d layer is much like a conv2d layer, except that it uses a simple maximum function instead of a kernel. The pool size parameter analogous to kernel size. Maxpool2d layer doesn't have any trainable weights like a convolutional layer does in its kernel, however. Let's take another look at the extraction figure from the last lesson. Remember that maxpool2d is the condense step. Put condense. Notice that after applying the rel function detect, the future map ends up. Let me load the exercises before continue reading. Notice that after applying the rel function detect, the future map ends up with a lot of dead space. That is, large arrows containing only zeros. The black area is in the image. Having to carry this zero activation through the entire network and increase the size of the model without adding much useful information. Instead, we would like to condense the future map to retain only the most useful part, the future itself. This in fact is what maximum pooling does. Pooling takes a patch of activations in the original future map, places them with maximum activation in that patch. So shifts the probabilities to 1, I guess. When applied after the rel activation, has the effect of intensifying futures. The pooling step increases the proportion of active pixels to 0 pixels. Apply maximum pooling. That said, the condensed step to the future extraction we did in the example in lesson 2, this next hidden cell will take us back to where we left off. We use another one of the functions in tf.nn to apply the pooling step, tf.nn.pool. This is a Python function that does the same thing as the maxpool2d layer you use when model building, but being a simple function is easier to use directly. So tf.nn.pool. Pool window shape, boolean type, padding, strides. Pretty cool, hopefully translation verse. Call the 0 pixels unimportant. Does this mean they carry no information at all? In fact, the 0 pixels carry positional information. The blank space still positions the future within the image. Maxpool2d removes some of these pixels. It removes some of the positional information in the future map. This gives a convnet a property called translation invariance. This means that convnet with maximum pooling tend not to distinguish futures by their location in the image. Translation is the mathematical word for changing the position of something without rotating it or changing its shape or size. Watch what happens when we repeatedly apply maximum pooling to the following future map. So original 16, 16, 88, 4, 4. The two dots in the original image become indistinguishable after repeated pooling. In other words, pooling destroyed some of their positional information. Since the network can no longer distinguish between them in the future maps, it can't distinguish them in the original image either. It has become invariant to that difference in position. In fact, pooling only creates translation invariance in a network over small distances, as with the two dots in the image. Features that begin far apart will remain distinct after the pooling. Only some of the positional information is lost, but not all of it. So it's pretty much like a zoom, and makes you lose accuracy of points that are near to each other. Unload this stuff. These, these inversion small differences in the positions of features is a nice property of an image classifier to have. Just because of differences in perspective or framing. The same kind of feature might be positioned in various parts of the original image, but we would still like for the classifier to recognize that they are the same. Because this invariance is built into the network, we can get away with using much less data for training. No longer have to teach it to ignore that difference. This gives convolutional networks a big efficiency advantage over network with only dense layers. You'll see another way to get invariance for free in lesson 6 with data augmentation. Conclusion in this lesson, we learned about, is this correct? We learned about the last step of feature extraction. Condensed with max pool 2D. In lesson 4, we'll finish up our discussion on convolution and pooling with sliding windows. Some of these texts seem a little bit wrong when I read them. Not sure because as if I'm not getting it or just a mistake. Which happens. Pretty normal to make mistakes when typing stuff. So just importing the initial stuff, decoding the image and resizing it, creating the kernel, converting the image to a float. We're gonna reshape. Image filter tf.nn conv2. So it already created all the other steps in this cell. Apply pooling to condense. For the last step in the sequence, apply maximum pooling using a 2x2 pooling window. You can copy this code to get started. So tf.nn.pool. Type is gonna be max, I think. The window shape is 2x2, but I'm not sure how exactly to write this. It's in parentheses. And here is supposed to be caps lock. But the next cell to see what maximum pooling did to the future. It intensifies it, everything. Learn about how max pool today layers give a convolutional network the property of translational invariance over small distances. In this exercise, we'll have a chance to observe this in action. This next code cell will randomly apply a small shift to a circle and then condense the image several times with maximum pooling. Run the cell once and make note of the image that results at the end. Size 64 by 64. So it's condensing a lot of times in this for loop. Tf reshape, tf pull, squeeze. I don't know what this is, but So original is losing resolution and zooming, pretty much. Suppose you had made a small shift in a different direction. What effect would you expect that have on the resulting image? Try running the cell a few more times. If you like, you get a new random shift. So it changes a bit on this image based off the randomness. See the solution. In the tutorial, we talked about how maximum pooling creates translation variance over small distance. This means that we would expect small shifts to disappear after repeated maximum pooling. If you run the cell multiple times, you can see the resulting image is always the same. The pooling operation destroys those small translations. Global average pooling. We mentioned in the previous exercise that average pooling has largely been superseded by maximum pooling within the convolutional base. There is, however, a kind of average pooling that is still widely used in the head of a convnet. This is a global average pooling. A global average pool 2D layer is often used as an alternative to some or all of the hidden dense layers in the head of the network. What is the layer doing? Notice that we no longer have the flattening layer that usually comes after the base to transform the 2D future data to 1D data needed by the classifier. Now the global average pool 2D layer is serving this function, but instead of unstacking the future, like flatten, it simply replaces the entire future map with its average value. Though very destructive, it often works quite well and has the advantage of reducing the number of parameters in the model. Let's look at what global average pool 2D does on some randomly generated future maps. This will help us to understand how it can flatten the stack of future maps produced by the base. Let's next solve a few times until you get a feel for how this new layer works. So vision tools dot random map determines the size, the scale, the K power. I assume the K power is how much it's gonna lose in accuracy. How much it's gonna simplify. I'm not sure. Future maps, they have shape, future map. Since each of the 5 future maps was reduced to a single value, global pooling reduced the number of parameters needed to represent these features by a factor of 25. Substantial saving. Now we move on to understanding the pooled features. After we've pulled the features in just a single value, does the head still have enough information to determine a class? As part of the exercise, we investigate the question. Let's pass some images from our car or truck dataset through VGG16 and examine the features that result after pulling. First, run the cell to define the model and load the dataset. So it's loading the image, creating the pre-trained base, attach a global average pooling layer after the base. Notice how we've attached the global to the layer after the pre-trained VGG. Ordinarily, VGG will produce 512 future maps for each image. The global average pool layer reduces each of these to a single value, an average pixel. If you like, this next cell will run an image from the car or truck dataset through VGG and show you the 512 average pixels created by global average. Run the cell a few times and observe the pixels produced by car versus the pixels produced by trucks. Let's see if I can already run this. Understand the pulled features. What do you see? Are the pulled features for cars and trucks different enough to tell them apart? How would you interpret these pulled values? How could this help the classification? After you've thought about it, run the next cell for an answer. I see hand first. So the thing is, I don't see the truck here. Oh, I have to run it a bunch of times. But I assume it's gonna be on the edges. It's pretty hard to just with the pulled feature maps to know the difference. Let me just check the answer. The VGG16 base produces 512 feature maps. We can think of each feature map as representing some high-level visual feature in the original image. Maybe a wheel or a window. Pulling a map gives us a single number, which we could think of as a score for the future. Large if the feature is present, small if it's absent. Cars tend to score high with one set of features, and trucks score high with another. Now, instead of trying to map raw features to classes, they had only had to work with these scores that global average pool should produce. A much easier problem for it to solve. Let me save this. Global average pooling is often used in modern covenants. One big advantage is that it greatly reduces the number of parameters in a model, while still telling you if some feature was present in an image or not, which for classification is usually all that matters. If you're creating a convolutional classifier, it's worth trying out. Conclusion. In this lesson, we explore the final operation in the feature extraction process, condensing with maximum pooling. Pooling is one of the essential features of convolutional networks and helps provide them with some of their characteristic advantages. Efficiency with visual data, reduced perimeter size compared to dense networks, translation invariance. We've seen that it's used not only in the base during feature extraction, but also can be used in the head during classification. Understanding it is essential to a full understanding of convolutions. So next one. You can close this. And still 7 left here. Still 41 minutes left. In the previous 2 lessons, we learned about the 3 operations that carry out feature extraction from an image. Filter for a convolution layer, detect with relo activation, condense with max pooling. The convolution and pooling operations share a common feature. They are both performed over sliding window. With convolution, this window is given by the dimensions of the kernel, the parameter kernel size. With pooling, it is the pooling window, given by pool size. There are 2 additional parameters affecting both convolution and pooling layers. These are the strides of the window and whether to choose padding at the image edges. The strides parameter says how far the window should move at each step, and the padding parameter describes how we handle the pixels at the edges of the input. I remember on the course where Brilliant, there are some, they show you some how this stuff is calculated. And it's pretty much function to the power of 2 of, I think, something multiplied by m minus n divided by height or by the width and multiplied by the other stuff. But I remember I couldn't understand really well. I understood kind of the way that it is. It's basically getting the dimensions and multiplying. You're basically iterating through the dimensions of the pooling given the dimensions of the whole image. So you have to find the how many times it's gonna perform this operation. And then each time is for each layer. So we have to multiply by the layers as well. It was something like that. But I remember it was a little bit complicated. And I don't think they're gonna touch on this course. They're just I think all the Kaggle courses are just talking about the libraries themselves, not the mathematics behind it. So it's probably not enough to create a very decent understanding of how it works. With these two parameters, defining the two layers becomes Kernel sequential layers conv2d. So from what I understand so far, they can have different strides because although they are related, they are not necessarily the same thing. Distance the window moves at each step is called the stride. We need to specify the stride in both dimensions of the image, one for moving left to right and one for moving top to bottom. This animation shows strides 2 by 2, a movement of 2 pixels at each step. What effect does the stride have? Whenever the stride in either direction is greater than 1, then the sliding window will skip over some of the pixels in the input at each step. Because we want high quality features to use for classification, convolutional layers will most often have strides 1-1. Increasing the stride means that we miss out on potential valuable information in our summary. Maximum pooling layers, however, will almost always have stride values greater than 1, like 2 by 2 or 2 by 3, but no larger than the window itself, obviously. Finally, note that when the value of the strides is the same number in both directions, you only need to set that number. For instance, instead of 2 by 2, you can use stride 2 for the parameter setting. Let me open the exercises, alright? Padding. When performing the sliding window computation, there is a question as to what to do at the boundaries of the input. Staying entirely inside the input image means the window will never sit squarely over these boundary pixels like it does for every other pixel in the input. Since we aren't treating all the pixels exactly the same, could there be a problem? But the convolution does with these boundaries values determined by a padding parameter. Tensorflow, we have two choices: the padding cosine or padding valid. There are trade-offs with each. When set padding valid, the convolution window will stay entirely inside the input. The drawback is that the output shrinks, loses pixels, and shrinks more for larger kernels. This will limit the number of layers the network can contain, especially when the inputs are small in size. The alternative is to use padding sane. The trick here is to pad the input with zeros around this border, using just enough zeros to make the size of the output the same as the size of the input. This can have the effect, however, of diluting the influence of pixels at the borders. The animation below shows a sliding window with same padding. The VGG model we've been looking at uses the same padding for all of its convolutional layers. Most modern convnets will use some combination of the two. Example, exploring sliding windows. To better understand the effect of the sliding window parameter, it can help to observe a feature extraction on a low resolution image so that we can see the individual pixels. Let's just look at a simple circle. This next hidden cell will create an image kernel for us. I'm gonna load this stuff before I continue. So it's pretty much just the kernel. here. The VGG architecture is fairly simple. It uses convolution with strides of 1 and maximum pooling of 2 by 2 windows and strides of 2. We've included a function in the Vision Tools utility scripts that will show us all the steps. That works pretty well. The kernel was designed to detect horizontal lines, and we can see that in the resulting feature map, the more horizontal parts of the input end up with the greatest activation. What would happen if we changed the stride of the convolution to 3? This seems to reduce the quality of the feature extracted. Our input circle is rather finely detailed, being only 1 pixel wide. A convolution with strides of 3 is too coarse to produce good feature map from it. Sometimes a model will use a convolution with a larger stride in its initial layer. This will usually be coupled with a larger kernel as well. The ResNet 50 model, for instance, uses 7x7 kernels with strides of 2 in its first layer. This seems to accelerate the production of large-scale features without the sacrifice of too much information from the input. Conclusion: this lesson we looked at a characteristic computation common to both convolution and pooling, the sliding window and the parameters affecting its behavior in these layers. This style of windowed computation contributes much of what is characteristic of convolutional networks and is an essential part of their functioning. So here it's already built. Optional experimenting with feature extraction. This exercise is meant to give you an opportunity to explore the sliding window computations and how their parameter affects feature extraction. There aren't any right or wrong answers, just a chance to experiment. We provided with you with some images and kernels you can use. Run this out to see them. So car, circle, Kaggle, okay. So these are the images and these are the kernels. So I guess these kernels are pre-made based on the models. So it's just matrix that were put on a library based on the model they they are best suited for. To choose one to experiment with, just enter its name in the appropriate place below, then set the parameters for the window computation. Try out some different combinations and see what they do. So put the image here, the kernel, vision tools, extraction. And then you can change the pool size stride and conv stride, I guess. I'm gonna test with gonna do the Kaggle K to see. On the kernel, I'm gonna choose emboss. Now let's change the conv stride to 3. Exponential 1. I'm gonna test a bunch of them, I guess. So this makes it a lot less accurate on the pulling. And the pull stride and pull size 5, just see the changes. So it loses resolution, but now it has a better picture. Let me change this to true. That looks better now, but still the same thing. So if I put this one, I guess it's gonna be higher resolution. Yeah, much higher. Let's test with 1. Yeah. So the smaller the values, the higher the resolution, I think. So this is almost done. The receptive field. Trace back all the connections from some neuron and eventually you reach the input image. All the input pixels a neuron is connected to is that neuron's receptive field. The receptive field just tells you which parts of the input image a neuron receives information from. As we've seen, if your first layer is a convolution with 3 by 3 kernels, then each neuron in that layer gets input from a 3 by 3 patch of pixels, except maybe at the border. Another thing I would like to understand is why it has to be a two-dimensional array. I guess that has to do with the way that the library performs calculations with the matrix and, through the inputs and hidden layers and outputs, but I'm not sure. It probably has to do with that, but I would like to know how it actually works. What happens if you add another convolutional layer with two-bit kernels? Consider this next illustration. Now trace back the connections from the neuron at the top, and you can see that it is connected to a 5 by 5 patch of pixels in the input, the bottom layer. Each neuron in the 3 by 3 patch in the middle layer is connected to a 3 by 3 input patch, but they overlap in a 5 by 5 patch. So that neuron at top has a 5 by 5 receptive field. Grant the receptive field. Now you've added the third convolutional layer with a 3 by 3 kernel. What receptive field would its neuron have? Run this up below for an answer. Oh, how is it possible to know? If we add the third by third, if added a third convolutional layer. Oh, if we add one more. So I guess it's just by the dimensions of each one, because they are connected. So they will have a 7 by 7 receptive field, because they overlap, so it's not going to be one for each one. So why stack layers like this? 3 kernels have 27 parameters, while one 7 by 7 kernel has 49. Do they both create the same receptive field? This stacking layers trick is one of the ways combinants are able to create larger receptive fields without increasing the number of parameters too much. You'll see how to do this yourself in the next lesson. Not completely sure if I understand. I think I do, but not 100% confident on that. Optional, one-dimensional convolution. Convolutional networks turn out to be useful not only two-dimensional images, but also on things like time series, one-dimensional, and video, three-dimensional. We've seen how convolutional networks can learn to extract features from two-dimensional images. Turns out that combinants can also learn to extract features from things like time series, one-dimensional, and video. This optional exercise, we will see what convolutional looks like on a time series. Time series we use is from Google Trends. It measures the popularity of the search term machine learning for weeks from January 25th to January 15th of 2010. Yeah. Okay, so we load this. So this is just the CV, then plotting. What about the kernels? Images are two-dimensional, so our kernels were 2D. Time series is one dimension, so kernels is 1D. Here are some kernels sometimes used on time series data. So the trend average is just a vector and converting to float. Convolutional on a sequence works just like convolution on an image. The difference is just that a sliding window on a sequence only has one direction to travel, left to right, instead of the two directions on an image. And just like before, the features peaked out depend on the pattern on numbers in the kernel. Can you guess what kind of features these kernels extract? Now comment one of the kernels below and run the cell to see. So they guess the relationship between each value, of course, but they're tracking to see if it's smaller and smaller numbers, or they tracking the trend basically, like the name says. In fact, the D-trend kernel filters for changes in the series, while Average and Spencer are both movers that filter for low frequency components in the series. If you are interested in predicting the future popularity of search terms, you might train a convnet on time series like this one. It would try to learn what features in those series are most informative for the prediction. Though convnets are not often the best choice on their own for these kinds of problems, they are often incorporated into other models for the future extraction capabilities. One problem I see with this is that you can have very high dimensional sequence of data that's interconnected with a bunch of other variables that are not necessarily represented to that data by itself, because you're compressing a high dimensional space into a 2D graph, because you have to relate two variables on the graph. And when you do that, you're losing all the accuracy from the connection of the data points that make up that time series. So even though the model can become good at predicting the time series, it will probably overfit because it doesn't have access to the high dimensional factors that make the time series be what it is. I think I'll be right back. I think I'm gonna finish this today, even though it might pass 2 hours because there's only two tutorials left. And this one has finished now. So let me see if I can run this. Examine the loss. That the training loss and validation loss stay fairly close is evidence that the model is just a memory of the training data, but rather learning general properties of the two classes. But because this model converges on at a loss greater than the G16 model, it's likely that it's underfitting some component infinite from some extra capacity. Okay, breath back. Okay, I'm back. I don't think this finished running. I think I'm gonna close this as well. Finish saving. It's probably gonna take a while. Now that you've seen the layers a Covenant uses to extract features, it's time to put them together and build a network of your own. Simple to refined. The last three lessons we saw how convolutional networks perform feature extraction through three operations: filter, detect, and condense. A single route of feature extraction can only extract relatively simple features from an image. Things like simple lines or contrasts. These are too simple to solve most classification problems. Instead, nets will repeat this extraction over and over so that the features become more complex and refined as they travel deeper into the network. Convolutional blocks. It does this by passing them through long chains of convolutional blocks, which perform this extraction. These convolutional blocks are stacks of complexity and max the layers. What's role is feature extraction we learned about in the last few lessons. Input, output. So I have the convolution, the relu, and the pooling. Each block represents a round of extraction, and by composing these blocks, the convenants can combine and recombine the features produced, growing them and shaping them to better fit the problem at hand. The deep structure of modern convenants is what allows this sophisticated feature engineering and has been largely responsible for their superior performance. Design a convenant. Let's see how to define a deep convolutional network capable of engineering complex features. This example will create a Kernel sequence model and then train it on our card's dataset. So NumPy imports everything. This part I still don't understand really well what's doing. I know it's randomizing the set for some purpose, but I'm not sure exactly how, where. I'm not sure if this is explain the training and validation set randomly. They didn't explain this as well. And I haven't seen on the other tutorials this exact function. Then separating the image for training, run validation with the batch sizes and converting them to float in this function. Def data experiment auto. Let me load the exercises. Find model. Here's a diagram of the model we will use. Let me run this. Conv2D max pool. Conv2D. So 3 layers of Conv2D max pool with different number of filters and same kernel size. Then a flatten to make the values to convert the outputs into one input. And finally the dense layers. Now we will define the model. See how our model consists of 3 blocks of Conv2D in layers, the base followed by a head of dense layers. And translate this diagram more or less directly into a Keras sequential model just by filling in the appropriate parameters. So Keras sequential, value same, input shape, height, width, color, channels. Give the input dimensions in the first layer. So the input dimensions are the input shape is the dimensions of the picture. Which goes on the first convolution. And then the last is classifier hand. Noticing this definition is how the number of filters doubled block by block. This is a common pattern. Since the max pool to the layer is reduced, yeah, this makes sense. Because you're reducing the image each time you max pool. And doing the zooming thing. So each time it's gonna be a higher resolution of the image. So you have to double the size of the filters. You can train this model just like the model from lesson 1. Compile it with an optimizer along with velocity metric appropriate for binary classification. So it's using the cross entropy loss function and add them as the optimization. Part pandas, then put into a graph. This model is much smaller than the VGG16 model from lesson 1. Only 3 convolutional layers versus the 16 of VGG16. It was nevertheless able to fit this dataset fairly well. Might still be able to improve the simple model by adding more convolutional layers, hoping to create features better adapted to the dataset. This is what we'll try in the exercise. So I already won the first one. Just setting up the data. Data matplotlib. Label bold, label size large, data weight bold. Then defining the training validation, converge float, auto tune. Design a convnet. Let's design a convolutional network with a block architecture like we saw in the tutorial. The model from the example had 3 blocks, each with a single convolutional layer. Its performance on the car or truck problem was okay, but far from what the pretend VGG16 could achieve. Might be that our simple network lacks the ability to extract sufficiently complex features. We try and improve the model either by adding more blocks or by adding convolutions to the blocks we have. Let's go with the second approach. We'll keep the block structure, but increase the number of convolution layer in the second block or 2, and in the third block to 3. So in the second block to 2, and in the third block to 3. So just adding a convolutional layer. And a dropout on the head. Try to prevent overtraining, I guess. Define model, give the diagram above, complete the model training, by define the layers of the third block. So block 1 has the input shape here, filters 32, 64. So it's gonna be these filters 128. Just double, same kernel size, vision rel, padding same. And then has an extra over today. And I guess it's before the max pooling. So maybe it's after. Oh, before. So I did something wrong here. I think, yeah, forgot the comma. Correct. Compile to prepare for training. Compile the model with an appropriate loss and accuracy metric. So model.compile uses the Adam optimizer, getting it from Kara's library, and the binary cross entropy loss function. What? So it's kind of weird the way that they did this. Because they did the same cell twice. Maybe this is a mistake here. Yeah, I think this was supposed to be the solution. Yeah, but whatever. Finally, let's test the performance of this new model. First run the cell to fit the model to the training. No, now it's gonna take ages again. And now run the cell below to plot the loss and metric curves for this training run. Let me see if this one saved. It's still saving. So I think what I'm gonna do is keep going while this runs. It's probably gonna take a while. It's probably gonna take even more time than the other one. Because it's 50 epochs. Train the model. So just checking. I'm gonna keep going to lesson 6. This is just gonna show the plot of the loss, the loss and the validation, loss and validation graphs. Data augmentation. Now that we've learned the fundamentals of convolutional classifiers, and I think I'm gonna stop this. It's gonna be a little bit more than 2 hours, but that's fine. Now that you've learned the fundamentals of convolutional classifiers, you're ready to move on to more advanced topics. This lesson will learn a trick that can give a boost to your image classifiers. It's called data augmentation. Usefulness of fake data. The best way to improve the performance of a machine learning model is to train it on more data. The more examples the model has to learn from, the better it will be to be able to recognize which differences in images matter and which do not. More data helps the model to generalize better. One easy way of getting more data is to use the data you already have. If we can transform the images in our dataset in ways that preserve the class, we can teach our classifier to ignore those kinds of transformations. For instance, whether a car is facing left or right on a photo doesn't change the fact that it is a car and not a truck. So if we augment our training data with flipped images, our classifiers will learn the left or right is the difference it should ignore. And that's the whole idea behind data augmentation. Adding some extra fake data that looks reasonably like the real data, and your classifier will improve. Using data augmentation. Typically, many kinds of transformations are used when augmenting a dataset. These might include rotating the image, adjusting the color or contrast, warping the image, or many other things, usually applied in combination. Here's a sample of the different ways a single image might be transformed. So just rotating the image. Data augmentation is usually done online, meaning as the images are being fed into the network we're training. So as the images are being fed, is making these changes. While the training is usually done on mini batches of data. This is what batch of 16 images might look like when data augmentation is used. Each time an image is used during training, a new random transformation is applied. This way, the model is always seeing something a little different than what it's seen before. So it's pretty much like the version of normalizing the data, or is rescaling the data, but for images instead. So that you make sure you find the global minimal when using the gradient descent. This extra variance in the training data is what helps the model on new data. It's important to remember, though, that not every transformation will be useful on a given problem. Most importantly, whatever transformation you use should not mix up the classes. If you're training a digit recognizer, for instance, rotating images would mix up 9s and 6. In the end, the best approach for finding good augmentations is the same as with most ML problems. Try and see. Training with data augmentation. Kernels lets you augment your data in two ways. The first way is to include. That's an interesting question as well. What's the boundary that makes one thing be what it is? So it's not so clear to me. And this is why I think this is still more of an art than a science when it comes to that. Because we pretty much have to use our intuition to judge what's the boundary that determines what something is. Yeah. But at the end, it's probably pretty much all the same thing, which is infinity. But So you can view neural networks as being a filtering process where they're finding the geometrical shape of things on space. Training of data augmentation. Kernels lets you augment your data in two ways. The first way is to include it in the data pipeline with a function like image data generator. The second way is to include it in the model definition by using Kernel's preprocessing layers. This is the approach that we'll take. The primary advantage for us is that the image transformations will be computed on the GPU instead of CPU, essentially speeding up the training. Let me load the exercises. In this exercise, we will learn how to improve the classifier from lesson 1 through data augmentation. This next hidden cell sets up the data pipeline. So import the stuff, create the random seed, matplotlib configurations, then load the image and validation dataset. Then here's where it's different, converting the image to the float. No, it's pretty much the same thing as before. The only difference is this label, I think. Define model. To illustrate the effect of augmentation, we just add a couple of simple transformations to the model from tutorial 1. So retain base false, model occurs sequential. Reprocessing random flip, which assumes flips randomly the image. Flip left right. Reprocessing random contrast. Contrast change by up to 50% base. Retain base. So first is reprocessing, then which is gonna be according to the batch size of the image. So here it's gonna be 64. So the data is gonna come on 64 batch sizes of images. It's gonna be pre-processed, then pre-trained according to the model on the ImageNet, and then it's gonna apply this model to the head. And it's gonna do this for the entire data, I think. Train and evaluate. Now we'll start the training. Then use the optimizer, add-on binary cross function, cause entropy, plus the data. Yeah. Training and validation curves in the model from tutorial 1 diverged fairly quickly, suggesting that it could benefit from some regularization. Learning curves for this model were able to stay closer together. We achieved some modest improvement in validation loss and accuracy. This suggests that the dataset did indeed benefit from the augmentation. So here's all the first steps. I think I'm gonna look at it. Explore augmentation. Uncomment the transformation and run the cell to see what it does. You can experiment with the parameter values too, if you like. The vector parameters should be greater than 0 and generally less than 1. Run the cell again if you'd like to get a new random image. So these are different preprocessing transformational training things. Different ways you can change the data, but keeping the. I wonder if I can do two of them at the same time. Probably yes. Yeah, so this changes left to right and horizontally. The transformation shows seem reasonable for the car or the truck data set. In this exercise, we look at a few data sets and think about what kind of augmentation might be appropriate. The reasoning might be different at what we discuss in the solution. That's okay. The point of this problem is just to think about how transformation might interact with a classification problem, better or worse. The Eurosat dataset consists of satellite images of the Earth classified by geographic feature. lower number of images from this dataset. So a bunch of pictures from the Earth. What kind of transformations might be appropriate for this dataset? That's a good question. Not really sure. Because if you change the vertically or horizontally, it's not gonna make much difference. Because they're not changing what the model is trying to predict. In the sense that it has to predict the horizontal and vertical values anyway. I think. Not sure. So it would have to be something that changes the image but still maintains the core aspect, which is that it is from Earth. So maybe the size? I don't know. Seems to this alter that flips and rotations would be worth trying for since there's no concept of orientation for pictures that thinking straight overhead. None of the transformations seem likely to confuse classes, however. So apparently rotation is fine. I think this one saved already. Not sure. Yeah, I'll close this. The Tensorflow flowers dataset consists of photographs of flowers of several species below the sample. What kind of transformations might be appropriate for the TensorFlow flowers dataset? So, first thing that comes to mind is changing the setting of the flowers, and then types of flowers, types, rotation, horizontal, vertical, that kind of stuff. The horizontal flips and moderate rotations would be worth trying first. Some augmentation libraries include transformations of hue, like red to blue, since the color of a flower seems distinctive of its class. A change of hue might be less successful. On the other hand, there is surprising variety in cultivated flowers like roses. So depending on the dataset, this might be an improvement after all. Now we use data augmentation for custom convnats similar to the one you built in exercise 5. Since data augmentation effectively increases the size of the dataset, you can increase the capacity of the model in turn without as much risk of overfitting. Add preprocessing layers. Add these preprocessing layers to the given model. So just copy and paste here. So random contrast, gonna change the contrast by factor at 10%. Gonna flip the image in horizontal, left to right, and rotate the image by 10 degrees. Now train the model, run the saw to compile it with a loss and accuracy metric, and fit the training set. So first sets the input layer, then the preprocessing, batch normalization. Using batch normalization, conv true, and next pull. 3 blocks of that. And the third with 2 convolutions. And then the head. Add them as the optimizer, binary cross entropy as a loss. Train model, examine the training curves, whether any what there yeah, this not sure if it makes sense. What there are any sign of overfitting? How does the performance of this model compare to other models you've trained in the scars? So this is gonna take a long time as well. Probably not gonna see it. That's all for computer vision. Ready to apply your knowledge. Check out your bonus lessons. You walk through preparing the submission for a competition while you learn how to train neural nets with TPUs. Kaggle's most advanced accelerator. At the end, you have a complete notebook ready to extend it with ideas of your own. With your first submission, so I think this is it for this course. I'm gonna wait for this to be over now. Just probably gonna take a while. So I'm gonna close the stream now and upload this to YouTube. Next, I'm gonna continue on the list of the Kaggle courses. How can I do this? Courses. Yeah, next one I'm gonna do time series. And I'm probably gonna come back later today to watch videos and study this stuff here on this list. What is power, relationship between power and electromagnetic field? Yeah, I'm gonna do this list here and then, so see you then.